Hello everyone, this is Anurag, and today in the ATCON-1 conference, I will be presenting my paper entitled Computational Time Complexity of K-Sum Problem Amalgamated with Quantum Search. Currently, I am an undergraduate at the Department of Computer Science and Engineering at Government College of Engineering and Textile Technology, Shirampur, Calcutta, India. This paper is co-authored by John Harshit and have been supervised by K. Lakshmanan sir and Professor Rama Murthy. This is a bit background of the work that I have put forward in this paper. So the K-sum problem, which is a generic member of the family of which two-sum problem and the three-sum problems are the younger siblings, is one of the most interesting problems in the domain of optimization techniques. Many researchers have shown that the K-sum problem can be solved in no less than order of n to the power of k minus 1. On the other side, many researchers have tried and successfully minimized its computational complexity, though quite negligibly. But since any subtle method don't exist to minimize its computational complexity, this K-sum problem have been added in the list of unsolved problem in computer science. In this research, we will try to analyze the computational complexity of this K-sum problem by exemplifying from the minimal bounds of quantum search by making use of the Buhrman's minimal bound in quantum search, and also we will be making use of the Grover search algorithm. So moving forward, this is the detailed introduction of the problem in computer science, and it's also about the mathematical optimization that we are using in this. So in computer science, mathematical optimization is selecting the best item from a set of all items. So we will be having some kind of criteria based on which we will be making this selection. So mathematical optimization, often known as linear programming optimization, is the process of choosing the optimal component among a collection of possible solutions to a given problem. Discrete optimization and continuous optimization are the two main subfields. According to a broader comprehensive perspective, a optimization issue entails either maximizing or minimizing a functional purpose by methodically selecting input values from a permitted set and determining the function's magnitude. A significant number of numerical methods is available for this optimization. So the problem statement of the K-sum problem is as follows. We will be given a list of n numbers. So let that be alpha 0, alpha 1, and it will go up to alpha n minus 1. We will have to select k numbers, alpha dash, alpha double dash, till alpha like k dashes. So such that the sum of all of these numbers should be equal to some specific value. Let's say that will be lambda. Now this lambda is the target that we are willing to hit. Now, this part is the main backbone of this research. This slide is mainly the backbone of the research. So, here we will be decoding the K-sum problem. Formally, if we see the K-sum problem by the advent of its searches, we can decode it by means of searching. It can be simplified to basic searches. So, what we were doing is actually we will be searching like K values from the set of n values, so such that the sum of all of these k values will be giving us the expected value, this lambda. So the time complexity of searching would be like searching only one element, then searching two elements, then searching three elements. Like this, it will go up to k. Now, phi n hereby corresponds to the computational complexity of searching algorithm that has been incorporated for this purpose. Now, generally, we make use of certain searching algorithms, let's say binary search or linear search, because of which we are getting this n to the power of k minus 1 complexity, and below which it can't be minimized further. So, this is a pictorial representation of the entire thing that we will be doing in this research. So, at first, let us suppose that we are having this n elements. From this, we will be searching one particular element. Let that element be alpha dash. Okay. So, from this, we will have to search like n places to get that give that alpha dash element. Now, this is the iteration 0, let's say. And then we are moving forward to iteration 1, in which now we have this alpha dash element, so we will have to find like k minus 1 element. So like n minus 1 places we will have to search, like the first place this alpha dash is been searched, so it's kept aside, and then we will have to search n minus 1 places. Further, if we move forward, it will be like n minus 2 searches, and after like n iterations we will be having only one place to search. So like if we sum of all of this, we will be getting the computational complexity. Now, By making use of the Buhrman search in action, we will be decoding this case problem. So, according to Buhrman, a bounded error quantum algorithm for searching of an ordered list of n items must use at least uh, log n upon log of n queries. Now, by making use of this Buhrman's minimal search, what we will be doing is we will be simply replacing this phi function over here by the Buhrman's search algorithm's complexity. So this particular summation could be solved, and by solving this summation, which we have shown in our paper, but due to the limitation of the slide numbers and everything, this time of presentation, we are not showing the computational part. So solving this summation, we will reach out to the asymptotes that the time complexity at its minimal would be log of n upon log of n minus k added with 3 upon 4 of log of n minus k upon n. A more tighter bound could be reached out by incorporating the theorems of Hadamard and Pauson. So this would lend us to this particular value, which can also be used later on. Now, by making use of the Grover search, like Grover search is another quantum searching technique. According to this Grover search, we can search a list of n items in the order of O square root of n. Now, by making use of this Grover search, computational complexity could be delineated as the summation. This I would go from 1 to k, and this entire thing, like the phi n part over there, which we have seen in the slide number 3 or such. So this could be replaced by square root of n. And again, by solving this summation, we would reach out to the conclusion that this would be order of log of n factorial upon n minus k factorial. Now, hereby, we would like to conclude our paper. So it's like the computational complexity of this K-sum problem would fall in this particular range. And this range is quite less in comparison to this n to the power of k minus 1. So it is quite observable from the extremum that the complexity could be dependent upon the selected value of k and n. Like if we are looking forward for three sum problem, then it will be comparatively less than that of 10 sum problem maybe. It is supposed to increase with increasing values of n and k. Now, the figures in the next slide basically shows the inequalities. So, this region, this red and this gray, the intersection of these two regions is the basic region in which the computation complexity is supposed to lie. And by means of this inequalities, we could definitely prove that it is much less than this O of n to the power of k minus 1. So these are some of the references which we have made use for preparing this manuscript. So that was all from my side. Thank you for allowing me to present this paper. I am open to your queries.